Hi everybody. Just wanted to give you a little bit of an introduction to error correcting codes. Error correcting codes are used to do what's called forward error correcting. Backward error correcting codes are, well, they're error detecting. So for backward error correction, what you do is you detect the error and then you go back to the transmitter and ask for a retransmission, but oftentimes that's not practical. So we consider forward error correcting as a mechanism whereby we build redundancy into the code word so that we can proceed to find enough information to correct any errors that occur during transmission. There's a mechanism called the Hamming distance, which indicates the total number of different bits. So if X is what you transmit and Y is the received code word, then the number of different bits here is equal to 2. D min is the smallest distance, that's Hamming distance, between any two vectors. If the transmission errors are less than the Hamming distance, then detection is possible. But that's detection. If L is equal to the number of errors, then we could detect up to L errors per word as long as D min is greater than L plus 1. So this is an invalid vector detection or error detection mechanism. So our problem is that when bits are transmitted through a noisy channel, they can be flipped. And when they're flipped, a 1 can be turned into a 0, and a 0 can be turned into a 1. And it's not clear which was sent, a 1 or a 0. And the goal of error control is to try and make the probability of an undetected error reduce. And so what we like to do is come up with some systematic mechanism for correcting the errors. So we take our data bits and we add some sort of check bits. And that means that we create a new code word which contains both the data bits and check bits. And so there are various notations which are used. Some people use M for the number of data bits and N for the total number of bits in the code word. It all depends on whose papers you're reading. So in general, we say that the weight of a vector is equal to the number of non-zero elements in the vector. So for example, here we're looking at the weight of vector 1101, and we see that it's equal to 3. So this is some scalar function of the vector, and the Hamming distance can be obtained by summing up all of the bitwise exclusive OR numbers and then adding up the number of ones, getting their weight. So if I take X exclusive OR Z, and that's a modulo 2 addition, we'll find out the total number of ones using the weight function, and that'll give us the Hamming distance. So here's the example. I take 1, 0 and do the exclusive OR with 0, 0. I get a 1, 0, which means there's just 1, which is equal to the number of different bits. So the minimum Hamming distance is the weight of the minimum vector, code word vector, which is to be transmitted through the channel, assuming X is not all zeros. So for a linear block code, we'd like to find the minimum Hamming distance as being the smallest number of non-zero vector weights. And so with the systematic codes, we come up with a notation. This is consistent now with the original paper from 1950 called the NM codes. That means N bits in the code word with M bits in the message. And so then if you subtract the number of bits from in the code word from the number of bits in the message, you get K, which is actually equal to the number of detection or correction bits. And so with the message bits corrupted, perhaps, we can devise a systematic mechanism to correct those errors. And so we have what is called some sort of redundancy, that is R, which is equal to the number of bits used divided by the number of bits in the message. And so this is typically expressed as N over M, where N is the number of bits in the code word and M is the number of bits in the message. This all comes about from Hamming, who originally devised it in 1950 in the Bell System Technical Journal, which you can find a paper for reproduced in Blackboard. So the NM codes typically have M less than N, and you can't have it the other way because you've got to have some kind of check bits. So that means that there are 2 to the M possible message bits, but there's 2 to the N possible code bits. And so for a block code, you want to find 2 to the M code vectors with a maximized Hamming distance. And so there's a kind of an intuition that goes on with error correcting codes. If you construct a code with a Hamming distance of at least 3, you have to have the ability to correct. You will have the ability to correct only a single bit error, but you can detect up to 2 errors with such a mechanism. And so what we do is we look to see if we can correct D errors if the Hamming distance is greater than 2D plus 1. So if you want to do 1-bit errors, then you need 2 plus 1, or 3 bits total for your Hamming distance. So the matrix representation of block codes is one that may be a little bit different from what you're used to. We start with a vector, and the vector is going to be some sort of code word. And we say that the code is linear if it includes the all zero vector and if it's closed under addition. So what that means is that Z modulo 2 with the code word is going to give you something of another code word. And so when we think about modulo 2 addition, we think about there's a little bug here in the slide I see. This has to be a 1. There we go. Fix that right there. We think about the standard exclusive OR operation. So Hamming codes are typically decoded by computing check bits with the parity sum, and then we arrange them as a binary number in order for us to obtain what's called a syndrome. The syndrome is obtained by a block matrix multiplication using a matrix called an H matrix, and that consists of an identity matrix adjoined with a parity matrix. We multiply that by the received code word, we obtain a syndrome, and we use the syndrome to determine exactly where the error occurred, and then we flip the bit by using an exclusive OR operation. So here comes Y, the code word, and here comes X, the transmitted message. And we can see there's a bit error here, and it's in location 0, 1, 2. So let's see what happens if we take X and modify it by adding, using modulo 2, the error. And what that does is it gives us Y. And if we take Y and do the inverse operation, take Y and modulo 2 it with the error, we get back to X. In other words, it's an invertible operation. So you can see the error here has caused the flip of the bit there. So here comes H transpose, which consists of the parity matrix adjoined with a K by K identity matrix. And you can see the identity matrix down here on the lower part of the transposed H matrix, and then you can see the parity matrix over in here right at the top. And this is the syndrome over here on the left, and what that does is it gives us a pointer to where the error has occurred. And so if you know that the error has occurred in the 0, 1, 2 spot, then you go over 0, 1, 2, and you can see that's syndrome number 3. So we can obtain syndrome number 3 by taking this H matrix, which is the P adjoined with the identity, and multiplying it by the Y, received code word. Once we have our syndrome, we're able to back out the error. Once we get our error, we're able to modify X in order to be able to get it back, modify Y in order to be able to get back to X. So typically what we do is we come up with a thing called a generator matrix. And the generator matrix will give us a code word by taking a message and multiplying it by the generator. And the generator consists of an m by m identity matrix adjoined with the same parity submatrix, an m by k submatrix. Once we have this generator in place, we do the modulo 2 multiplication against the message and get a transmitted code word. So it's a message adjoined with check bits. So that's the partition notation. We'll call it a partition vector. So the message bit vector and its check bits together come to n bits, and that's the m bits plus the k bits. A code vector can be obtained by this so-called, I'll say, matrix multiplication, but in fact what we're doing is a bitwise and then we're summing the columns together in order to get an exclusive OR weighting. So then the generator matrix is something that we can easily obtain during the transmission, but we won't need that in order to do a decode on reception. All we'll need is the H matrix. So here's the example. We've got a redundancy, n bits divided by m message bits, so it's n bits in the code word. K is going to be equal to or greater than 3, and then we've got a minimum Hamming distance in our 7-4 code. To make the P matrix, we use Hamming's rule, so we let the m rows of P all have 3-bit words with 2 or more ones in any order. So here are the 2 or more ones, and we can pick any order we like, and then we adjoin it with an identity matrix, and I see there's another blemish here in the matrix. That should be an identity matrix, right? There you have it. So now we've got the generator matrix. We've got to multiply by the message that we'd like to send in order to obtain a code word. So we have to formulate a message now. So let's take the check bits and do the multiplication, and that's going to give us a series of different check bits for each message. And once we do these multiplications, it's exclusive OR operations. We can simply write out all the messages and all the code words, and we can do all that computation in advance for all the different possible messages and all the different possible code words. For a 4-bit message, well, you can have 16 code words, but here's the first 8. And so then for syndrome decoding, you want to take the Y vector as the vector received after distortion in the channel, and you assume that X is not equal to Y, that is, the transmitted is not equal to the received. The converse is not always true. You may or may not have things cause errors. So then here's a mechanism for obtaining your syndrome. You multiply by the H matrix. That's the P parity partitioned with the K by K identity matrix. And then that'll give you a syndrome, which you then back out to give you an error vector. And then you take the, since X has been used, since the error vector was used to modify X in order to get Y, we can now use the error vector to modify Y in order to get back to the original code vector X. And we do that with modulo addition. That's bitwise exclusive OR. The one exclusive OR with 1 gives us 0, and so we're back to the original message. And so this is a mechanism whereby we can do syndrome decoding. Here's your H matrix again. Here comes the message. You can see what happens in here. 0, 1, 0, 1, 0 is multiplied by this column. We'll call it column 1. Here's column 1. Here's the bitwise multiplication. When you multiply these things, you're really doing an AND operation. You AND all the bitwise ones together, and you get a single 1 that comes out. And you add this together using modulo 2 addition. You do the same thing again here. There's 1, 2, 3. If there's an odd number, then the number will be 1 at the end, modulo 2 addition. 1, 2, and that's it. So 1 plus 1 is none because it's exclusive OR with the Boolean. And then we have, let's see now, 1, 2, 3, 4 ones. And so that's going to give us, oh, I see what we're doing here. We're doing an exclusive OR with the error that comes in. We found the error using the syndrome. We do the exclusive OR operation, and we get back to the original code word. There it is. So what we like to think about when we do these Hamming codes is we like to think about how to distribute the parity bits in the code word itself. And you can put the bits anywhere you like. It's often the case that if there's a long string of bits, you may have some error which is bursty that occurs in the middle of the code word. But in the algebra, it really doesn't matter where the parity bits go. And that's my little presentation of Hamming codes. Thank you very much for your attention.